Well, Mr. Sam's.
Hey, how's it going?
Hey, what you drinking today?
I got me a nice, tasty Coke. Thought I'd recharge my batteries a little bit.
Do you know how much sugar's in that thing?
Well, I can look it up, probably.
Yeah.
140 calories per one can.
That means like
39 grams of sugar.
I think it's like 3/4 of it's sugar.
But it's yummy.
You know what I'm drinking? I'm drinking a vitamin water.
Oh, yeah?
Yeah, vitamin water's better for you.
Oh, yeah?
How many calories you got in that thing?
140.
140?
Yeah, what do you got?
240.
Ah! Ha, ha, ha.
Yeah, but mine's twice the volume. Mine's actually got like healthy stuff in it.
Like what?
Well, let's see. I bet it's got like tartaric acid or something in there.
So if I just put vitamins in here, would that be healthy?
I don't think so.
No?
It's got cane sugar, crystalline fructose, okay, calcium lactate, that's for your muscles and stuff, right? Citric acid, monopotassium phosphate, what do you got?
High fructose corn
Oh,
syrup,
that's
caramel
the bad
color,
stuff. Oh, I'm
phosphoric acid.
Mm.
Oh, but the big one at the end, caffeine.
Caffeine. Yeah, I've heard that caffeine's not so good stuff. Well, I know you're drinking the Coke, but last time we've been talking to you folks, we were making batteries, right?
Mm-hmm.
So this is podcast 17.1. We're learning about batteries. So, Mr. Sam's, I know that the last time they couldn't really see it.
Yeah.
I think you were like
had
not
a problem.
doing. Yeah, you had problems. And
Yeah.
so I wonder if we should like make a battery again so they can see what it really looks like.
Yeah, let's give it a shot.
What do you think? Should we
Yeah,
do that?
let's
All
do it.
right.
Okay.
All right, Mr. Sam's. I see you've got your stuff.
Yeah,
there.
I got my little battery guy here. Now, again, I've got these two little wires coming out, and these are going to charge my my clock that's going on here. I have 2 empty cups, so let's just fill those guys up with some nasty Diet 7-Up. But Diet soda's disgusting, so here we go. You don't get those sugar and all the empty calories, but this has aspartame in it.
Aspartame.
It gives me a splitting headache for some reason. I don't know what the deal is, but it always gives me a
right.
headache. So anyhow, we got this going. And now notice one of these is made of zinc and one of these is made of copper. Here's my zinc.
Let me
Here's the
zoom
copper.
in on there. Okay.
Okay, and that's very, very important because those are metals and we get electrochemical reactions. So I'm going to put copper in one and I'm going to put zinc in the other one. And voila, we have nothing.
Oh, you need that old salt bridge?
Yeah, we don't have
You gotta have the salt bridge.
And we're actually, this one doesn't need a salt bridge.
Actually, it's really not a salt bridge.
No,
We're
this
getting
one just
serious,
needs to
actually.
complete the circuit. Okay, so what we're going to do is we're going to put a zinc in the other one. Now, by putting a zinc and a copper in one of them, I essentially have 2 of the half cells going on in one thing, and this is another thing of 2 half cells. So I really have 2 batteries that are hooked up in series here. So don't confuse this with the normal galvanic
Let
cell
me
that I'll
zoom
show you
in
here. in a minute.
here. Just
So there's enough stuff in our soda here to make the metals undergo an electrochemical reaction and produce enough voltage to make our little clock go.
there we go.
Ta-da!
How
You've
cool
got
is
the
that?
little flashing 12, just like your VCR if you unplug it. VCR. Anybody know what a VCR is anymore?
What's a VCR?
I don't know. Wow, I'm starting to feel old. Okay, so there's our double battery clock. Now what I'm going to do is I'm going to do this a little more on the chemistry side of things. I'm going to take our
Why don't you sit down? To
couple
do
little
this?
clips. You want me to sit? All right.
Yeah, then you won't be so tall.
I can do that. All right, so just got to take a little cup, and this is a cup made out of ceramic. Now, yesterday we talked to you about the little porous disc. This is basically our porous disc. This is going to also double as our salt bridge. It's going to allow ions to pass through it. Okay,
So,
I'm
you
gonna
put it in a cup? Oh, that's
that
like
in
it's a
there.
regular drinking
Actually,
cup.
Yeah. It is. I'm actually going to do this in stages so I don't get my hands all yucky. All right, this one's zinc chloride, ZnCl2. I'm just going to pour that in here, and I should really be wearing safety glasses, shouldn't I?
You really should, Mr. Sam's.
Yeah.
In fact, we should probably go get those.
I
Actually,
think I
our
will.
wonderful assistant is going to get
Maybe Chris,
is going to get us some safety
my
glasses.
chemistry friend, can throw me some chemistry glasses. Those green ones right there on my desk would be grand.
Perfect.
Look at that.
Should not be working with chemicals without your goggles.
I'm a bad
You are very
person.
bad. Your eyeballs are going
know.
to burn off your face, and that would be very bad. Oh,
Copper 2 sulfate. So this is a source of copper ions. The zinc chloride that I had is a source of zinc ions.
Probably good right there.
Okay, so I have copper ions out here, and I have zinc ions in here. Now what I'm going to do, I'm just going to put that in there. Now I've got a piece of zinc, and I've got a piece of copper. I'm going to make sure the copper one goes in the copper solution, and I'm going to put the zinc one in the zinc solution, and we're going to see what happens. So we're going to hook this guy up. Let's kind of get me a level here. All right, it's going to have to go down a ways. Hey, look, our bell's ringing.
Think of it.
Okay, and then I'm going to put the zinc one here inside the little cup.
Now, why don't you turn that more profile, Mr. Sam, so we can see better?
There you go.
Maybe a little bit to the left so I can. The metals are now
Your left or
visible.
my left?
Either way, yeah.
Okay, so I got the copper in the copper solution, the zinc in the zinc solution. Now, I've got my salt bridge. I've got my two cells. I've got the cell on the outside and the half cell on the inside, each with a half reaction of the redox going on. Okay, but what am I missing, Mr. Bergman?
I think you're missing a wire. You need a wire.
I need a wire. I need something to connect the two half cells, so I'm going to take this little guy here. Now, I could just take one wire and I could connect one side to the other side, and voila, I have a battery. But it's better if I actually hook it to something that I can see that I have some current going through here. So
why don't you put that in the front? Oh,
yeah,
good.
this is an old school voltmeter or a galvanometer. Yeah. Now it doesn't quite set right at 0. It's setting kind of at like a little bit above 2.
I'll zoom in on it.
Yeah. No, I'm going to hook this up here, and
it worked.
look at that.
Why don't you disconnect it and connect it so we can see it?
Connect it again. So it's a little bit above 2, and now it's going to go a little bit above 1. So I've got.
What actually that means, folks, is that you're actually making like probably about a 1-volt system.
Yeah,
which is actually what we would have predicted previously. So.
Yeah, and we'll talk about the math about that later. But this, essentially, guys, is a battery. And we could take a whole bunch of these. If we hooked them up all together in series, we could get 9 volts. A whole bunch more in series, we could get 18 volts and have a grand old time.
Thank you very much for the demo, man! Mr. Sam's the demo god.
Giddy up.
Okay, so we're back. So this is our podcast. You've seen a little demo at the beginning, and so now what we want to do is we want to go ahead and start talking about this stuff.
There we go.
All right. This is the chart. Actually, we're having some problems with our chart, I think, yesterday.
Yeah.
And this is the chart that's in your textbook. So if you open up your textbook, remember we're using the Zumdahl textbook. This is table 17.1. So, folks, we want you to use table 17.1 as you do this, okay?
Yep, have it out.
All right. Now we want to talk about something called cell potential and equilibrium.
Yep.
Now, we've learned about equilibrium before.
We have. That's the big K.
All right. But first, before we do that, actually, we need to talk about there's a connection between the voltage, which we learned about last time, and delta G.
Yep.
Okay, does that make sense now? Is that if you use this equation, negative NFE0. Now, we need to define some terms here, Mr.
Yes,
Sams.
we do.
I think we need to figure out what the heck is an N.
N is going to be our number of moles, and in this case, it's moles of electrons.
And how do you determine that, though?
You're going to have to look in your two half reactions when you balance your redox equation. We always multiply by an integer to get the number of electrons to be equal, and once you have them equal, that's your number of moles of electrons.
All right. So the way I like to say it is the moles of electrons that cancel from your half reactions. Yep. So if like one's got 2 electrons, and on the other half reaction it's 5 electrons, of course you would have to multiply this one by 2 and this one by 5. And how many electrons would that be?
That'd be 10.
So then N would be 10.
Yeah.
Sometimes it's 2, sometimes it's 1. And F is a funny thing too.
Yeah.
F is called a Faraday. Named after Michael Faraday, one of the coolest scientists. I love his story. We won't go into it, but it's very cool. And a Faraday is 96,485 coulombs per 1 mole of electrons. Now, a coulomb is something we haven't learned about. If you take physics or are taking physics or have taken physics, coulombs measure charge.
Even if you haven't taken physics, they still measure charge.
Yeah, but if you might know something about it because of the charge, right? Because of So a Faraday, okay, is this, and you'll see. Basically, you multiply, and a coulomb is a joule per mole or something. Okay, and E naught, what's that?
Or something. That's your electrical potential of your cell.
Yeah, that's your volts, folks.
Yep.
So that you get from that table that we just saw a minute ago.
Yeah, when you stick your two half reactants together.
And you got like this one maybe, and this one maybe one you have to flip over, and then you get your...
Just like we did in the last lesson.
Just like the last lesson, yeah. So you're good on that, I think. All right. So let's see if we can find delta G for this reaction. So what's the first step, do you think?
I'm going to say split it up into half reactions.
Okay, so let's split it up into half reactions. So I've got the iron, and it's going to go to iron 2 positive. I see the iron here going to the iron 2 positive, plus 2 electrons. I do not have to play any nasty games like oxygens and hydrogens.
Nope.
And then the copper 2 positive is going to go to copper, and that'll be plus 2 electrons. I like this one because guess what?
It's 2 and 2.
The electrons cancel, so N in this case will be 2. So it'll be Fe plus Cu2 positive. You don't actually need this, but
No,
for
we
the
already have
react
it above it.
plus, oh yeah, Fe2 positive. It
now it's
canceled,
balanced.
but we didn't know that it would actually balance. Right. And so now we do need to look up the values for the voltages for this.
Yes, we do.
So let's go back a couple of
table.
screens. And so we have copper to copper plus 2.
Uh-huh. So let's see. Where is that one? Right.
No,
nope,
that's the wrong one. Oops, I have the wrong ink color for this, don't I?
Still looking for copper. You guys have probably already seen it right now. Why can't they see it? Oh, there it is, second from the top on the right-hand side.
Point 34 for the copper one. Okay. So the copper one is 0.34. The iron to iron 2.
Okay, now this is, well, we're going to see those iron 2 to iron, so we're going to have to flip this one because these are all reductions.
I see it right here, Mr. Sam.
There it is. Yep, so that's negative 0.44, but we need to flip it, so it's going to be positive 0.44.
0.44, so that adds up to 78.
0.78, yep.
Now, folks, we're going to use this cool equation. Delta G equals negative NF E naught.
Yep. Now, shouldn't there be a little zero above that G as well? Since it's standard electrical potential, should be our standard.
Now, we are making an assumption. What assumption are we making?
That everything is at standard conditions. 1 molar solutions and 25 degrees Celsius, 1 atmosphere.
N was 2, right?
Yep.
Times F, which is 96,485.
I don't know why I remember that number.
And then E naught is 0.78. Now, I'm not putting units on there, but we'll put it at the end here. And you get a big number, Mr. Sams.
1.5.
Negative, right?
Yep.
Negative 1.5.
0.517.
0.517. That's way too many significant digits.
Yeah,
By the way, that's going to be in joules per mole. So if we divide by 1,000, you get negative 151 kilojoules per mole. I could do that in my head.
Yep.
All right. So that is the value of delta G.
There it is.
Not terribly difficult.
Not at all.
Okay. Now, what happens? So that's how you solve for delta G.
Yep.
Okay. All right, so on that last problem, folks, we found delta G, right? We found delta G to be negative 151 kilojoules per mole.
G with a little zero on it.
Yeah, thank you.
Yep.
Now, one thing that we've already kind of talked about this in our last unit in Chapter 16, but I want to make sure you can make this connection, folks. And we forgot to put this in your handout, so why don't you're going to have to add this. Okay? So if I want to solve for K, you might remember an equation from Chapter 16, which is delta G naught is equal to negative RT natural log of K. So if I know the value of delta G naught, I can solve for the equilibrium constant K. Remember, for double arrow reactions, right? Well, so I can say, now, the important thing to note here is this isn't kilojoules per mole, but R, what's R? It's 8.3145 joules per Kelvin mole. So I've got to convert this to joules.
Yep.
So I'm going to say negative 151,000 joules per mole is equal to negative 8.3145, I'm not going to put the units in there, times the temperature. We have to pick a particular temperature, so let's say 300 Kelvin or something like that.
Sure. Times
the natural log of K. Now, how would I algebraically solve that?
I would say divide both sides by 8.3145 and 300.
Now, when you do that, folks, actually negative.
Yes.
Make sure that you divide on your calculator. Yep. Do not say divide and then times.
Unless you use parentheses.
Unless you're using parentheses appropriately, yeah. And so what do you get there?
60.5.
We have a negative and a negative, and so that makes it a positive. So 60.5 is natural log of K. And so you have to take e to the 60.5 to get rid of the natural log. You get a big number.
You're going to get 1.95 times 10 to the 26th power.
That's a very high number. Now, what does that mean when you have an equilibrium constant that's that large?
That it's insanely spontaneous.
Yes.
It just goes.
Yes. So K, if K is very bigger than 1, very bigger than 1. If it's much larger than 1, then the products are favored. In this reaction, they are very, very favored. Okay? All right. Now, what are we going to talk about now?
The Nernst equation.
Nernst. Mr. Nernst. That sounds like a weird name. Nernst. All right. Mr. Nernst said, what happens if you don't have standard conditions? What if it's not 1 molar?
Yeah.
And 1 atmosphere and such? Well, guess what? There's this equation. It's the Nernst equation.
Nernst.
And so if you have a different concentration, E, notice there's no 0 on this E. This E is equal to the E0. That's the number from the standard. And this is essentially over here the correction factor. Now, R is a constant. F is a constant. N is those moles, and T is the temperature. But if you assume a couple of terms, you can assume, for example, if you assume that R and T, if you assume that T is 25 degrees Celsius, R, T, and F are all constants.
Yeah.
And so this right here, if you assume 25 degrees Celsius, you can rewrite the equation, and it looks like this. Now we need to talk about what this Q business is.
Q is your conditions that are not standard.
Or your reaction quotient?
Yeah, you're just going to plug in the concentrations. It's just like K, where you have products over reactants, except instead of using the equilibrium products over reactants, you're going to use
the non-equilibrium.
The given products over reactants.
So here is a particular problem. We have a reaction here that I think we need to do balance first. Yeah. Yep. What is the electrophilic cell with the following concentration? So I need to balance this equation. Well, not exactly.
We can even just look them up on our
We can say VO2 positive goes to VO2 positive. How's that for you? Okay, but now we can go back to that table.
Yeah.
So if we go back to the table, I can find my VO2. This is the one we couldn't find. Here it is, down here.
About halfway on the left-hand side.
Yeah, I think I see it there. All right, so they're right about here, and it's 1 volt.
1.0, look at that.
So now I go. So have you got it down, Mr. Sams? So you guys know where we're going to get this. Mr. Sams got the book out, and we'll just use his book. So what are our options there? Tell me the whole reaction.
You want the whole reaction. Okay. We're going to add 2 hydrogens and 1 electron to the left.
Plus 2 hydrogens and 1 electron?
Mm-hmm.
On the right?
And on the right, we need 1 water.
Water. Okay.
Okay.
And our second reaction, that was 1 volt, right? Was it written? Is it 1 or negative 1?
1.00, positive.
Okay.
As written.
As written. And then the zinc.
Yep.
Zinc. Is going to go to zinc 2 positive.
Yep.
Plus 2 electrons, and we can. That's actually, I don't have to do any math on that.
Yep. And that's in the
you
book.
Flipped it.
Yeah. In the book, it's negative, so we're going to do positive 0.76.
So the voltage is looks like
1.76.
1.76 volts. Now we do need to then add these reactions, right?
Yep.
So this one we're going to double because we have to get the 2 electrons to cancel. So this will be 4H positive plus VO2 positive.
2 of them.
2 of them, I knew that. Plus the zinc metal makes the zinc 2 positive plus VO2 positive.
2
of them, I knew that. Plus 2 waters.
Just making sure. Just check.
All right, now we have a balanced equation.
There it is.
Now the reaction quotient will be the products over the reactant.
Right, and those are given to us here.
So zinc 2 positive times VO2 positive squared because of the 2 here. Now what do we do with the water there?
It's not really going to participate.
Why?
So, it's not an aqueous thing. These need to be homogeneous equilibrium. So,
so this needs to be
dealing with
AQ.
ions.
And so then we'll say VO2 with a positive 1 charge, kind of weird how that works, times the hydrogen to the 4th power. And the zinc is a solid, so we ignore that. So this is the Q, and if you look up here, we're given all these numbers.
We're just going to plug those numbers in.
So we're going to just plug these numbers in, and we're going to solve for Q.
Plug and chug. Should we...
The zinc 2 positive, 0.1, all right? The VO2 positive, I'll get my things right, is 1 times 10 to the minus 2 squared. I think we'll just find Q first. I think it'll be easier.
Yep.
And the other VO2, the one with a subscript, is a 2 molar, and we'll square that. And the hydrogen concentration is 0.5, and we'll take that to the 4th power. So, Mr. Sams, when you get that on your calculator?
Yep, I got 4 times 10 to the negative 5th.
So it's 4 times 10 to the negative 5th. Okay. So here we have, what was that number again, Mr. Sams?
It's 4 times 10 to the negative 5th.
So Q is 4 times 10 to the minus 5th. Now our equation was E equals E naught minus 0.0592 over
N was...
Now let's go back, take a look. N was 2 electrons it canceled, right?
Mm-hmm.
So we'll say over 2. Is it log or natural log?
Natural log, ln.
Times the natural log. Are you sure?
That's what it says on our handout.
Is our handout wrong?
I don't know. Let me look it up in the book. I forget.
Okay, so we just looked in your handout and it's wrong. It should say log of Q.
Yeah. Now, let's clarify. The actual Nernst equation, E equals E naught minus RT over NF natural log of Q is
Let's
correct.
Go back to that screen.
Yeah, that's correct. Whoop, that one is
this
right
is
there.
correct.
That one's correct.
This
one's wrong.
Is wrong. This should
that should say log.
LOG.
Our mistake. Please fix that.
All right. Sorry about that, guys. We just figured out our mistake on the handout, and we've already made copies of it. So now we just plug it in, right?
Yep.
So I would take the log of 4 times 10 to the minus 5.
Yep.
I would do that first. Do this first, guys. Times it by 0.0592. Actually, E naught, it was 1.78, right?
It was, what was it, 1.7? Yeah, I think so.
I'll double check while you're typing it in. 76. 1.76. So this will be 1.76 minus, and we'll figure out this entire term. This whole thing, what does it come out to be?
The whole thing is negative 0.13.
Oh.
So it's 1.76 minus negative 0.13.
Negative 0.13, and when you add that up, you get
1.89.
1.89. Now, actually, I want to talk about that for just a moment. Notice that the voltage went up.
Yes.
You can actually understand this in Le Chatelier principle perspective. Now, if our concentration of our hydrogen was, I'm going to put it on the this is 0.5 molar. The VO2, this is 2 molar. The zinc was
0.1.
0.1, and the other one was a small number.
1 times 10 to the negative 2. So
1 times 10 to the minus 2. These numbers over here are bigger than these numbers. That's going to drive the reaction to the right. So if the reaction is driven to the right based on the concentrations, the voltage will become higher than the regular voltage. If it's the reverse, if you were to have big numbers over on the reactant side, then you would have a smaller voltage.
Yep.
So that's something to actually think about. This all is kind of connected to things we've learned previously.
Right. And this is just kind of some steps for doing exactly what we just did.
We just did this, and so, write a balanced equation. All right, find E naught, use the Nernst equation, and plug in the concentration values for Q. All right. Now, there is something called a concentration cell that we should chat about.
Now, earlier, or up to this point, we've been talking about 2 different half reactions going on in each of the half cells. So what we're going to show you now is when you have the same half reaction going on in each of the half cells, however, they are at different concentrations.
So let's say I'm making a solution. Let's take silver. How about it? So we take a piece of silver, and in the other solution I put a piece of silver. And in each of these I put silver ions. Let's say silver nitrate. What am I missing, Mr. Sams?
You need a wire.
Need a wire. We'll put a V here for the voltmeter that hooks them up. You get very good at this.
Oh, yeah.
So the reaction at the anode will be Ag positive, or actually I'm not sure what to think about it, goes to Ag plus an electron. So he's going down. This is the cathode reaction, actually.
Yes.
So this is the
Reduction
cathode.
happens at the cathode. Red cathode.
And at the other one, it's going to get Ag. It's going to go to Ag positive plus an electron. Wait a second. Does this work?
Yeah.
Yeah, it does. Ag positive plus Ag. Now,
if they were at the same concentration, it would not work because there's no gradient there.
So
things in nature like to be the same, and if they're already the same, they're going to stay there.
So let's say for the sake of argument that the right cell is 1 molar,
Okay.
and the left cell is 0.1 molar. Okay.
All right.
What will our voltmeter read?
Let's see here.
So what we need to do is we need to do the Nernst
Yep,
equation.
do the Nernst.
Let's assume we're at 25 degrees Celsius. How many electrons cancel here?
And which side did you assign as the cathode, and which side did you assign as the anode?
That didn't. We have to figure that out, actually. I think we need to figure that out.
Yeah, I think you're right, because we only got to figure out which direction the electrons are going to move.
That's right. All right, Mr. Berger made a mistake, so the picture looks a little different, but this is, I made a mistake. Okay, what's the voltage if we go back on that table and look?
The voltage on the table for the silver ones?
Yeah, so we have to go back to the silver because we've got to find that E naught term, right?
Yes, we do.
And so I think it's like 0.8 or something.
Where'd my picture go? There we go. Okay, silver, that's plus 2.
It's like 0.8, isn't it?
0.8? I think you're right. Yep, 0.8.
So this is 0.8.
You've been doing this a while.
Which one is which?
What?
Which?
The reduction potential is 0.8.
All right, then what would be this one here?
That would be negative 0.8.
Well, when you add those up, they add up to 0 volts.
Yep.
So this isn't going to work.
Well, if they were both at 1 molar solutions, it wouldn't work. But our left-hand solution there is a 0.1 molar.
Oh, I see. So we can use the Nernst equation.
We can.
So if we say E is equal to E naught minus 0.0592 over N times the log of
Q.
Now, what's Q going to be in this case?
Well, it's products over reactants, but we need to figure out which one is the product and which one is the reactant.
Well, it's just going to be silver over silver, right?
Yeah.
So let's just write silver over silver. There's no coefficient, so it's just going to be the concentration of silver or the concentration of silver.
Mm-hmm.
So this is going to be equal to 0 volts minus 0.0592 over 1 times the log. Now we've got two choices. There was 1 molar and 0.1 molar. Which way is it going to be? It's actually better to think about it for a moment.
Yeah.
Le Chatelier's principle says, if you want to have positive voltage, we talked about this earlier, which side do you want to have the higher concentration?
The product side. Reactant side.
That would be the reactant side. So this needs to be 1 molar, and that makes this the 0.1 molar.
Yep.
So when we do this on our equation that's products over reactants, this needs the log of 0.1 over 1.
Okay.
And that comes out to be...
Log of 0.1 is -1, so then we're going to take that times 0.0592 and then divide it by 1 because the n is 1. So we have...
0.0592 volts?
We do.
Yeah, I had to figure that in my head. Yeah.
Yeah, sorry, I'm staring at my
Mr.
screen here.
Sams was doing a classic, student mistake. He was using his calculator when he could have figured it out.
Should have been using my brain.
Yeah, he needs the brain, Mr. Sams. You need brain cells up here. Okay. All right, so...
I have small children. They consume most of my brains.
Now, that's not a very high voltage, but it would produce a small voltage. That's called a concentration cell. Now, going back to this just briefly, let's make sure. Now, if this is the 1 molar side, the 1 molar side is being...
that's our reduction. Reduction takes place at the cathode.
So this is the cathode, and so if we were to label this, this would be the positive side, and this would be the anode, and it would have a negative side. And while we're at it, let's
electrons always go from the anode to the cathode.
See, electrons will go, as this picture is drawn, from the left to the right, and that would mean that the through the salt bridge, the cations will flow, right? Because we get...
Yeah. So
and through the salt bridge this way,
anions will flow.
The anions will flow. Okay?
Ta-da!
I think we've made a concentration cell.
So.
Hey, batteries.
Yeah,
what are batteries? Hey, basically a battery is very simple. A battery is just a galvanic cell hooked up in series.
Yeah. I mean, you can just have one galvanic cell. Yes. And that makes a battery.
Yeah,
I mean, as we've seen, most of these you get a voltage of around 1 or maybe 2 if you're really lucky. But how do you make a 9-volt battery? Well, you just take a bunch of 1.5 volters and you stick them together.
That's exactly right.
Hook them together.
All right, and this is a picture right here of a lead-acid battery. This is the kind that's found in your car. And if you look at this picture, you've got the cathode here. The cathode is made of PbO2. You can see the reaction down there. And then the solution, basically the salt bridge, they're all actually immersed together. And so instead of separating them in separate cells like we have before, you actually have separated them by the pieces of metal.
Right, and this is exactly what we did with the cups of soda and the clock that we hooked up. We had the cells all submerged in one solution, and then we just stuck 2 of them together.
Because if I'm not mistaken, a car battery is 12 volts, something like that. And you can't make 12 volts with those reactions on that table. And so they just put lots of them together, and they all add up to a total of 12 volts. Yeah. Now, if you were to take this is just an alkaline battery right here.
Yeah, this is how your little AA's, AAA's that you have in all of your portable devices, calculators.
What's intriguing about this is if you look right here, is that essentially you've got the red is the anode, just a piece of graphite rod.
Yep.
And then they seal it with something, insulator. And then they have a paste. Now, we've been doing solutions. When you did the example in the podcast a little bit earlier, you had, they were aqueous solutions.
Yeah.
But paste is sort of an aqueous solution. It's just thicker.
It's basically your salt bridge, isn't it? Your electrolyte paste. It's kind of like the porous cup.
Yep, and the outside is a zinc container, and guess what? You've made a battery. So so you've separated them in a little battery, and then of course the electricity can go out this way or and in this way. I can't remember which direction it flows, but yeah, physics people know that. Now another thing that's intriguing that we can talk about. Another thing that we can talk about is corrosion. And so I have here a picture of, or not a picture, an actual piece of metal. And you're seeing the picture. And what we've got here is just an old piece of corroded metal. And it's it's rusted. And so how does rusting occur? It's actually an oxidation reduction reaction that we can talk about. So let's take a look at the picture in the screen, and that will help us figure this thing all out. So what we've got here is this is how this particular piece of metal got rusted. So this is like a piece of metal right here, and usually it happens with some water. And what happens is that you get a water droplet, which creates a aqueous solution.
Mm-hmm. And in that water, there's generally some oxygen dissolved.
Yes, or something's dissolved in the water.
Mm-hmm.
This actually has to be some kind of salt of some variety. So if there's any kind of a salt that works, that's why salt water causes this corrosion to work so much faster. And so what happens is you create this water, and you actually create a couple of cells. And at the anode reaction, you get the iron turning to iron 2. And if there's oxygen present, which of course in the world, on the Earth, there's plenty of oxygen, you get this reaction. So you get these two half reactions to go in, and it works.
Yeah.
So that's how corrosion works.
This is my favorite.
Yeah, this is actually a pretty cool discussion. Another thing that you can have is you got a buried pipe, as in pictured in this picture.
Pictured in this picture.
Yeah, is a iron pipe. It's going to corrode because the water's moist, or the ground's probably moist from rain and
that
this
tends to
and
cause
that.
problems. You know, you have like water mains break and things like that.
Yeah, that happened recently
It
here.
did.
Yes, and people canceled school. Yeah,
Yeah,
kids
although it
probably
wasn't
like
a
that.
metal pipe. I think it was probably PVC. But
Yeah.
anyhow.
Oh well. But if it was a metal pipe, it would corrode, and eventually it would just go away. In fact, I've heard that some cities like Chicago and New York, they've got all these ancient pipes which were metal, and they're now corroding, and they got problems.
Yep, and they
And
do
they're
this
like
with boats.
hundreds of feet under the ground.
They do this with boats in the ocean too.
Yeah, let's talk about that in a minute.
Yeah.
All right. So how do you make sure this doesn't corrode?
Well, you turn it into a cathode.
So if you can make this the cathode, what happens is they took an anode, they add a piece of a more active metal, and magnesium is the classic one that they use.
Yes, it's called a sacrificial anode because we're sacrificing it. Okay, you just have to make sure you replace them often enough.
Yeah, let me tell you a story. My father used to own a boat, 50-foot boat, or yacht, I guess. He lived on it. Did I have a picture of that? No, I didn't. In his boat, of course, was a big boat. Okay, it had a propeller.
I guess that's a boat. Oh, there's the propeller. Okay, now it's
all right. It had a propeller, and he bought the boat. And before he bought the boat, he checked the boat out to make sure that it was in good shape and this and that. The one thing he didn't do, because it was expensive, which cost him more money, as you'll see, is that this particular propeller was starting to corrode. It was in the ocean, and that was a problem. Because what they do is they take and they add actually a big piece of magnesium for the sacrificial anode. And guess what? The magnesium had already been destroyed, or had been used up, so to speak. Because as time goes on, the magnesium gets smaller and smaller and smaller.
Yeah, that's the one thing we haven't really talked about is the anode actually, it goes from a solid to an ion. Because that's the oxidation. Oxidation takes place at the anode. So you notice the solid magnesium becomes an ion, so eventually it'll corrode away. But on the cathode, the metal is actually deposited to the cathode. So it's going from an ion to a metal.
Yeah. And so the magnesium gets used up, and it was all used up. And so basically I think it was like $4,000 or $5,000 to replace the propeller. Because it was like 50-foot boat propeller, and they had to like lift up the boat onto 50-foot boats. Lifting them up on a dock is not cheap.
No.
And so and they put a new, and I guess these items right here, $20.
$20 and some guy with a scuba suit to hook it up, right?
I think so. Actually, I think you just it's not hard. I mean, so it might have cost him $100 to do it, or versus like $4,000.
I believe that's called a stupid tax.
Yeah, that was yeah. So he made a mistake. So now, folks, all right, I think we're done. And Mr. Sams, you are still drinking that nasty soda.
I am. I've been picking away at it. It's
I've
almost
still
lunchtime.
got a little bit of my vitamin water, and I think I'm going to take a swig of it.
All right, swig away. I'll take my
I
high
think we're
fructose
done.
corn syrup because
Oh!
of caffeine.
Yuck!
I like caffeine.